Hello, astronomers. Newland here. Hertzsprung-Russell diagram time. We discussed anti-jump cannon and the Harvard classification scheme, oh, be a fine gorilla karate me. And we've discussed the importance of the Harvard computer group, the women at Harvard that really sort of ushered in astronomy as a modern science. And Henry Norbert Russell and Ejnar Hertzsprung were two astronomers who used anti-jump cannon's uh, thinking, and actually anti-jump cannon's letters between Ejnar Hertzsprung and her. They actually helped shape this plot that is so common in astronomy. So, what is it? I'm using here the University of Nebraska Lincoln old Flash version of the Hertzsprung-Russell Diagram Explorer because it is so perfect for this particular purpose, even though getting it to run on your own computer means you got to download something, and that can often be a hindrance. So, what is it? So, if we plot the for a particular star, its temperature as you see on the x-axis, and the luminosity of that star, in this case, in relationship to the sun, um, on the y-axis, then you'll notice patterns start to emerge. So here's my little demo star, and I can drag it around the XY plane here. Luminosity here. So a thousandth the brightness of the sun, all the way up to 1,000,000 times the brightness of the sun. And notice that because here, I'll put that on there. Be a fine gorilla karate me. The Canon Harvard scale on the x-axis goes in that order. The longer wavelength starts, well, you start with a shorter wavelength near the origin, so that would be blue, all the way through whatever Roy-G-Biv backwards is, to red on this end. So the wavelength increases along the x-axis, but that means the temperature increases towards the origin. So you get hotter as you get this way, and cooler as you go that way. And dimmer is towards the bottom, and hotter is towards the top. And notice as I drag, that's the word, the sample star around inside the HR diagram, over on the left-hand side is a little model of what that star might look like compared to the sun in terms of radius, in terms of color. Remember, color is temperature. And the luminosity is actually not really indicated by the size in this particular, or there's nothing in our little toy model there that compares the luminosity. It's just about the size of the other star compared to the sun. So this thing is interactive. You can change the temperature here. You can change the luminosity there. Again, this is in terms of solar luminosities. So that's 7.5 times brighter than the sun. Or so you can grab this thing, and that's what it means down here. That's why it's R with a circle with a dot in the middle. That's R sub sun and T sub sun. Remember that sigma T to the fourth is the luminosity. L equals sigma T to the fourth. It also equals 4 pi R squared. So it's not just the temperature along the x-axis. It's also these these diagonal, I guess, green lines for solar radius factor. So any star along this green line here is the same size as the sun, one solar radius. Any star along this green line there is about 1/10 the radius of the sun. Any star here is about 100th the radius of the sun, 1,000th, then 10, 100, and 1,000. Okay, so again, the temperature varies. The luminosity varies as 4 pi r squared, which is the surface area of a sphere, times sigma t to the fourth. So when you do that, patterns start to emerge. So this red, here, I'll put this back here. This red line is what we call the main sequence. Any star that is plotted on the main sequence of an HR diagram is said to be fusing hydrogen into helium. So any star we plot that's not on the main sequence means that it's not fusing hydrogen into helium. It's either fusing a heavier element into something, or it's not fusing anything at all. So what I'm going to do is I'm going to put the nearest stars I'm going to check that box and notice how many of them are along the main sequence. And the fact, remember that the way radius works, radius increases down here at the origin would be small compared to the sun, and heading this way diagonally up, they get bigger and bigger. So this would be sort of like the radius axis. So don't get confused about that. And the temperature axis is you get cooler as you go to the right and hotter as you go to the left. And luminosity is dimmer than the sun on the bottom, brighter than the sun on the top. Okay, so anything along this line we call a dwarf star. Any main sequence star, we're going to essentially say that stuff in this range of one, well, from about a tenth to about 10 times the radius of the sun, that technically counts, and just in terms of size, as a dwarf star. So anything on the main sequence is going to be a dwarf. Whereas, if we here, let's turn on the luminosity classes, and I'll tell you what those are. If we were to plot for our star, it's maybe it's a type K, which will put it over here, and it's about 1,000. There we go, 1,000 times brighter than the sun. Notice, by the way, how much bigger it must be. So that means it's big and it's cool and it's not fusing any hydrogen into, or that's not the main way that it's producing energy. It's not fusing hydrogen into helium as its major energy source. Any star that's on the main sequence, so this red sort of zone, those stars' main source of energy is fusing hydrogen into helium. Okay, so then there are a couple other categories. There are the supergiants up here, blue supergiants, yellow supergiants, and red supergiants. Wait, where are yellow ones? Sort of, I guess, here-ish. There we go. So this whole section is blue. And this is a logarithmic scale. If you've already done the HR diagram coding lab, we've discussed this already. But if you need to plot L equals sigma t to the fourth, then it would make a lot of sense to take the log of t to the fourth so that you don't, all your data is not all on one end or all on the other end. You can sort of spread it out. So this is a logarithmic scale. And the same with luminosity. Look, 10 to the 2, then another power of 10, 10 to the 3, another power of 10, 10 to the 4. So this is what's known as a log scale, because that makes it easier to see patterns in the data. Whenever you have data that a small change in one thing, like the temperature, yields a really big thing in another thing, like the luminosity, then it makes a whole lot of sense to plot that data as a logarithmic plot. And if, by the way, instead of the luminosity, we did this as magnitude, magnitude is already a logarithmic plot. Remember that Hipparchus, upon which we built the system, he didn't realize that it was orders of magnitude that he was referring to when he compared stars to the brightness of Vega, which is what we would think of as a magnitude of 0, at least on the apparent magnitude scale. Now, on the absolute magnitude scale, we're not using the same sort of reference. We are sort of assuming that all stars are about 10 parsecs away. So on the absolute magnitude scale, stars are sort of uniformly thought of as being 10 parsecs away. Then we think about how much light would reach us as the observer. So absolute magnitude and luminosity are very similar. By having luminosity on the y-axis, you could also put absolute magnitude, and notice that the plot didn't change at all when I changed the scale changes a little bit. Again, magnitude is already logarithmic in nature, whereas luminosity, they've got these little dots or the dashes, the tick marks on the y-axis getting closer and closer together. That's an indication you're looking at a log plot. And the same with the spectral type. So we were looking at the supergiants, and notice how it stayed blue for so long as I'm dragging this over here, because it's actually a logarithmic scale. Okay, so anyway, so we've got the choices of temperature along the bottom axis. Remember, hotter is to the left, bluer is to the left, cooler is to the right, redder is to the right. So temperature, which is also color, but you can also use anti-jump cannon's spectral type. Then there's another thing here called B minus V color index, which I think I'll talk about separately. Then there's this category. So we've got the dwarfs, which are the main sequence stars. We've got these stars that have moved into this red giant cloud. These are giant stars. They're not fusing hydrogen into helium as their main energy source, but they could still have other kinds of fusion going on. The sun will one day leave the main sequence, and if we were going to plot it, it'd end up over here. And then eventually stars will go through a pattern where they're no longer giants. They'll end up as white dwarf stars down here, incredibly small, not fusing anything into anything, and they are stellar remnants. So that's yet another grouping. So we have the dwarf stars, we have the white dwarfs, you have the giants, and then you have the supergiants. Okay, so we talked about the luminosity growing as you go up the y-axis. The spectral type and color run towards the origin, so bluer and hotter over here, redder and cooler over there. And technically, it's shorter wavelength on the left and longer wavelength on the right. So what happens if instead of the nearest stars, which mainly are small and red and on the main sequence, what happens if I pick the brightest stars instead? So notice that's the benefit of the HR diagram. By plotting a group of stars, you can see patterns between them. So we still have stars that are on the main sequence when we plot the brightest stars, but they're now big. They're bigger, they're hotter. They're not necessarily a whole lot bigger, I guess, but they're hotter than the sun for sure. And that tells us something very important. So one of the things to think about as you look around the night sky, the brightest stars, there are some here, we'll hit overlap. There are a few that are bright and close, but most of the bright ones are pretty far away, whereas most of the near ones, the reason they are bright enough to see in our sky is because they're pretty close by. Here, we'll put them both on there at the same time. The red dots represent the overlap stars. The green dots are the ones that are nearest, and the blue dots are the ones that are brightest. And notice when we are looking at this now, having both data sets plotted at the same time, or I guess all kind of three, we've got a bunch of stars along the main sequence, which most stars in the Milky Way are. We have some stars over here in this red giant cloud. We have some that we don't really know how to categorize without some more information. We have some that are clearly blue giants, and although none in this data set show up, there are easily white dwarf stars in the nearby Milky Way. So if you're looking at the HR diagram coding lab, you'll notice that there were stars down in that category. So the benefit of the HR diagram is by having the luminosity on the y-axis and the temperature/color on the x-axis, patterns emerge if you plot lots and lots of stars together. There's the main sequence, the giants, supergiants, and white dwarf stars. The radius increases from the origin up and to the left. Luminosity or magnitude, remember negative magnitude is brighter, goes up on the y-axis, but temperature actually goes back the other way. Okay, hopefully that's enough that we can remember what's going on with the HR diagram.